from the mathematical point of view, what we want to do is just to have a canonical random geometry in the plane or the sphere in 2 dimensions. And of course, there are strong motivations from physics that you know better than me. And the method we are going to use, well, just standard method. We replace the sphere. Instead of working on the 2-dimensional sphere, we will work on the discretization, meaning that we will consider a graph drawn on the sphere, so what we call a planar map. And essentially what we do, we choose such a planar map uniformly at random in a certain class, and we view this object as a metric space by equipping the vertex set to the graph distance, and then we pass to the limit when the size of the graph tends to infinity. Okay, so we let the number of vertices or number of edges, if you prefer, tend to infinity. After rescaling of the distance, we hope to get the limit a continuous metric space and random metric space that will be the Brownian map. Okay? And of course, this simulation is supposed to give you an idea of what the Brownian map is. We come back to that later. And today I also want to say a few words about recent work in progress, in fact, with Nicolas Curien, which tells us that if we do local modifications of the graph distance, if we assign a random length, for instance, to the edges of the graph, in the scaling limit, we will still get the same object. And this was mentioned briefly by Timothy in the previous lecture. Okay, so of course, all this is very similar to what one does to define Brownian motion. You can view usual Brownian motion, purely a random continuous path. You can view it as a scaling limit, of course, of random walks on the lattice, but you can take many different scaling limits, and under suitable conditions, you will always get Brownian motion. And here it's a little bit similar. Actually, we can start from many different classes here of random planar maps. After rescaling, there is a universal object of the map. Okay, so this was just for the presentation. And now, maybe in the first part, I will recall the basic convergence result to the Brownian map. So this is just to remind you of the definition of a planar map, so maybe I will go fast for that. So here, for instance, I have a triangulation of the sphere. So I will always deal with rooted objects. So there is a distinguished oriented edge here in my planar map, the root edge, and the root vertex is the tail of this root edge. And I'm going to be interested in this lecture in particular in triangulations, where all faces, connected components of the complement of edges are triangles, or in the case of quadrangulations. And also, most of the time, I will allow, in fact, general planar maps. I will allow loops and multiple edges. So even in the figures, usually I will draw no loops. Okay, so this is a large triangulation of the sphere. Essentially, well, of course, here it's not represented on the sphere; it's represented in space. So you can see the triangles, one and so on. So I don't know exactly how many triangles you have there, but maybe hundreds of triangles, and you see, see a kind of fractal properties of the object that you get. And of course, if you are drawing this object on the sphere, there are parts of the sphere where you would see very few details because, triangles would be too dense in certain parts. So this is the reason why it's represented in space here. Okay? So the idea is just to build a continuous model from such a large triangulation by using the size 10 to infinity.
You don't have any limitation on the assembling of this triangle or the size?
Well, essentially I'm going to deal with the triangulation with a fixed number of faces. I'm going to let the number of faces tend to infinity. Yeah, so I'm going to make this more precise. So, in order to pass to the limit, I'm going to deal with planar maps viewed as metric spaces. Yes, I have a planar map, capital M, with a vertex set, and I equip the vertex set with the graph distance. Okay? So, well, just to remind you of the definition, the graph distance between two vertices is just the minimal number of edges on the path connecting these two vertices. So for instance, here I've represented the distances from the root vertex, which is this vertex at distance 3. Okay? So in this way I get for a simple metric space, in some sense, a finite metric space. But now I'm going to let, as I said before, the size of the map tend to infinity. So in order to do that, I first need to explain how I choose my random planar map. So here I will consider the set of all p angulations with n faces, where p is an integer at least equal to 3. So for p equals 3, it's the set of all triangulations. And of course, since I don't recall that, because on the previous slide, we are interested in only in this the combinatorial object. We look only at we identify two p angulations, they correspond via a direct homomorphism of the sphere. So there is only a finite number of possible shapes, so this set M and P is going to be finite. And what I want to do, I want to work with a fixed value of P, then P equals 3 to work with triangulations, and to let N tend to infinity. Okay? We could do something more general, in fact. We could, here I'm going to choose Mn uniformly at random in this set, so a uniformly chosen triangulation with n faces if P equals 3. We could do something more general, and we could deal with Boltzmann distributed planar maps, as Timothy was mentioning before. Here I will stick to this case here. Okay, so what we do, we look at then at the vertex set of this random p angulation equipped with the graph distance as a random compact metric space. Okay? And we want to deal with convergence of such objects. So in the first stage, I'm going to look at convergence in the sense of the Gromov-Hausdorff distance. Okay? So just a brief reminder of the definition of the Gromov-Hausdorff convergence. If you have a sequence En of compact metric spaces, you say that it converges if you can embed all your spaces isometrically. Of course, isometrically is very important, in the same big space, so that the embeddings converge for the usual Hausdorff metric on compact sets. Okay, so this is a Gromov-Hausdorff convergence. Now, using that, I can state the main result of convergence to the Brownian map. So this is just to recall the definition. I have my set of all triangulations with n faces. I choose one uniformly at random, capital Mn, and I look at the vertex set equipped with the graph distance. Okay, and the theorem says that, at least for these two cases, but I will say more about that later, at least if p equals 3 or if p is even, then the vertex set equipped with the graph distance rescaled by the factor n to the power minus a quarter, and also rescaled by this constant Cp that depends on p, converges to a uniform limit in the Gromov-Hausdorff sense. This limit is called the Brownian map. And of course, an important feature is the fact that the limit here does not depend on p. Okay, this is the reason why we put the constant Cp here is just to have uniqueness of the limit. Essentially, what is important is the fact that the rescaling here is by n to the power minus a quarter. Okay, so what is the meaning of this convergence? It's a convergence in distribution. Okay, it's a weak convergence if you want. If you are not familiar with convergence in distribution for random variables, you can think also of an almost sure convergence, okay? Saying that outside a set of probability 0, these random metric space converge to this one in the Gromov-Hausdorff sense. Okay? So to get an almost sure convergence, well, you need, in fact, to choose properly the sequence Mn. Okay? So this is why, in general, you have only convergence in distribution. Okay? So I should immediately say that when I obtained this theorem, the case p equals 4 was obtained also independently, in fact, a little before my work, by Grigoryan, case of quadrangulations. Since then, there has been extensions to many other classes of random planar maps, always with the same limit here, the Brownian map. I mentioned in particular that Marielle Bank and Luigi Adario-Berri have announced recently that this holds even for odd values of p. So it should hold for all values of p. Okay, briefly two properties of the Brownian map. It has outer dimension 4, almost surely. But however, it is almost surely homomorphic to the two spheres. Okay, so you should think of it as a two-dimensional sphere, but equipped with a very wide metric in some sense, which gives a factor dimension equal to 4. So maybe a slide of motivations. So of course, there are many motivations from different areas of mathematics and also from physics for the study of random planar maps, or of planar maps in general. And there are many motivations from combinatorics. I will not say more about that. Motivations, of course, as you know from theoretical physics, started with, well, I think planar maps were first used in physics in combination with expansions for matrix integrals, going back to the work of Toft and the celebrated paper by Breza, Itzykson, Parisi, and Zuber. And okay, this connection I can also mention in more recent work, in particular by Brownian. And of course, as you know, there are large random planar maps are also used as models of random geometry. Okay? And in this connection, well, there are many references I should give, but as you mentioned, there are a number of important papers by Jérémy Goutier and Emmanuel Viter, which so motivated part of my work in this area. I also mentioned the work by Bertrand Duplantier and Scott Sheffield, which is, in fact, a different approach to quantum gravity, to UV quantum gravity, I should say, which is based on the Gaussian free field. Okay? And this work has been followed by a number of other papers. I mentioned here the paper by François David, Kupiainen, Rod, and Vargas, and which, well, it relies on this Gaussian free field approach, but which gives a number of very interesting conjectures, saying that this approach would be closely related to the approach via planar maps. Okay, from my point of view, there are also very good motivations from probability theory. One would like to get a model for something that deserves to be called a Brownian surface, purely a random surface, which should be of interest to probabilists. And this should also be related to other very interesting recent developments due to Miller and Sheffield, and some of them also with Bertrand Duplantier, in particular concerning this new object called the quantum Lovener evolution, which should be very closely related to the Brownian. Okay, I will not say more about the motivations. Maybe a couple of slides also about how the Brownian map can be constructed. I just say that it arises at a limit of discrete object, but of course you can also give a direct construction of the Brownian map. Okay, and the construction is made from another important probabilistic object, which is a Brownian continuum random tree, also called the CRT. Okay, so what is a CRT? Well, I have a problem with my simulation. Well, the CRT is, well, it's also a universal limit, scaling limit for many classes of discrete trees. And it can also be obtained as directly, without doing any scaling limit, as a random continuous tree or real tree, which is coded by a Brownian excursion. So here there should be a picture of the CRT, but it does not appear for some reason. Okay, it's not so important. The idea is that, what do I mean by coded by Brownian excursion? It means that if you explore the tree, starting from a vertex which you can choose at random, in fact, and you explore it in clockwise order, there is a planar structure in the tree. The distance from the root vertex row here will evolve like a Brownian excursion. That's the meaning of the code. Maybe I should go to the next slide. So you should imagine that the CRT is something like this, but of course it's much more complicated. There are infinitely many branching points everywhere and infinitely many leaves. But imagine that the CRT is something like that. So how do you construct the Brownian map from such an object? So it's a tree like this. You can draw it in the plane if you want like this. Well, there are two steps. The first step is to equip your CRT with labels. Okay, so T is my notation for the CRT. And for, well, P here refers to the Brownian excursion E, because I view it as a tree coded by a Brownian excursion. So it has a distance E. And you assign a label ZA to each point, each vertex of your tree. Okay? And essentially, your labels are, well, you can view them as Brownian motion, linear Brownian motion indexed by the tree. Okay? Meaning that at the root, well, it's a centered Gaussian process. At the root, the value will be 0. And if you look at the variance of the increment of the labels between two vertices A and B, this will be simply the distance between A and B in the tree. Okay? It just meaning that if you move away from the root, okay, following a segment of the tree, your labels evolve like linear Brownian motion. In fact, it's true for any segment of the tree. Okay? So this is the first step. You assign labels to vertices of the CRT. And once you have done that, there is an identification process. You identify two vertices A and B. If they have the same label, but you require much more than that. You require that when you go from A to B around the tree, so you can do this either clockwise or counterclockwise, but let's say clockwise, for instance, like this. You encounter only vertices with label greater than or equal to the label of A, which is equal to the label of B. Okay, so on my picture here, I'm going to identify A and B. I'm going to glue, if you want, A and B. If for any of the red vertices that are here, the label is at least equal to the label of A, which is equal to the label of B. If you have this property. Okay? So it's a very strong property. In fact, you do not identify many vertices. When you do this identification procedure, well, you take the quotient space after these identifications, you indeed get the Brownian map. Okay? But of course, I should also define the distance. The distance is not too difficult to define, but it's a little technical. I will not do it here. Okay? Oh, so here, the simulation has come back. So this was the simulation of the CRT. And so this is, okay, so of course it's not an isometric embedding here. It gives you some intuition of what the object here. So what you do, what you really do, you identify certain pairs of points, like this, and so on. You glue the CRT onto itself, and
and actually it's not all.
Okay, so so this was the meaning of the next slide. Okay, this is just to give you an intuition of what the Brownian map is. And the reason why you can construct the Brownian map from trees goes back to bijections between planar maps and trees, and due in particular to Gilles Schaeffer, but there are also more general versions of these bijections due to Jérémy Boutier, Philippe Di Francesco, and Emmanuel Guiter. Okay, so let me come to the second part of the lecture, which will be in fact related to the previous two lectures, in fact, by Asaf and Timothy. So maybe I can remind you very quickly of the definition of the UIPT. We saw that already this afternoon. So the UIPT is the limit of uniformly distributed triangulation within faces. Written here. And of course, it's a limit in a completely different sense now than the one I had before. And before that, I was dealing with the Gromov-Hausdorff convergence, and I was rescaling the graph distance. Here, it's a limit in the sense of local limits. Okay? So I think Asaf called them Benjamin-Schramm limits. Okay? So it's just saying that if you look at the ball of radius r in the finite triangulation delta n here, well, here, it's important to have a good definition of a ball. So I define it as a union of all triangles that are incident to a vertex at distance smaller than r in the root vertex. Okay? So I view it also as a planar map, this ball. And of course, it takes only countably many values. And so the meaning of this convergence is the fact that if I look at the distribution of the ball of radius r, it will converge to the distribution of the ball of radius r in the limit, delta infinity. Simply meaning that the probability that the ball of radius r is equal to a given planar map M will converge to the same probability for the ball in the limit. Okay? So this is the definition of local convergence we already saw this afternoon. Okay? So this is just not a simulation, but a kind of artistic representation of the IPT. You should think of a planar lattice made of triangles in a random way, in some random way. Okay? Of course, there are many interesting questions you can ask about this object, and one question, of course, is about the recurrence of random walk on this object. This was, in fact, a long-standing open problem which was solved only recently by Gurevich and Narmias. It was also mentioned by Asaf in this lecture. Okay, so let me come to the more geometric properties of the UIPT. And well, I'm going to be interested, in fact, here in hulls, the UIPT. So what is a hull? I already defined to you the ball. Here is the ball of radius 2 in my example. So the ball of radius 2 here, you see, is just really, you have all triangles that have at least a vertex at distance smaller than 1 from the root vertex. Okay, you can check that all the blue triangles here on the figure contain a vertex at distance at most 1 from the root vertex. Okay? So what happens, of course, in these random lattices is that the complement of the ball is not going to be connected, okay, in contrast to these regular lattices. Okay? So here you have, of course, an unbounded connected component, but you have also two bounded connected components. And the hull is obtained simply by filling in the holes. Okay? You add the ball with the holes. Okay? So this was the ball, and this is the hull. So why am I studying the hull? Well, it turns out the hull is easier to study. You can get much more explicit results for the hull. Okay? So what do we get? Here is a result about asymptotic distributions for the perimeter and volume of hulls. Okay, so really I wrote it as a convergence of processes in T. So you look here, I look at the whole process of perimeters and volumes of hulls when the radius varies, but I rescale the radius. Okay, so I multiply here the radius by n, and I use this as a process in T. Okay, so and the proper rescaling of this now. Well, the perimeter is of order n squared, the volume is of order n to the power 4. Of course, it's the same 4 as in the Hausdorff dimension of the Brownian map, if you want, saying that essentially balls are going to have a ball of radius n will have a volume of order n to the power 4. Okay, and you can get a convergence distribution of this pair of processes. And you can describe the two limiting processes by saying that x, well, I'm not going to give a precise description, but it's basically a time-reversed branching process. Okay, so here it's a branching process taking values in the set of real numbers, positive real numbers, called a continuous state branching process. And such processes are characterized by their branching mechanism, which is here given by this function, which means that it's essentially something which does not have finite variance. It's something which has heavy tails, and okay, I'm not going to say too much about that. I will come back to this time revert here because it's important, but you should remember that perimeters are linked to a certain branching process. We'll see that later also. And essentially, the interesting object maybe is the perimeter first. Once you know the scaling limit of the perimeter, this capital X, you can write down explicitly also the scaling limit for the volumes. Okay? So what you get is a process which can be obtained in this way. Of course, volumes are increasing. Okay? The volume is increasing with respect to the radius. So this is an increasing process, and it increases only by jumps. Each time this process X has a jump, the volume process also has a corresponding jump given by the square of the jump of the perimeter process times the random variable psi here, which is distributed according to this density. Okay. So, okay, maybe I'm not going to say more about that. Something that's interesting is that you can have explicit formulas, in fact, for the laws, the asymptotic laws of perimeters and hulls. So I've written here, if you want, the asymptotic Laplace transform for perimeters. So it's very simple. This is just a gamma distribution, quite standard. The asymptotic distribution for volumes, well, you can also write explicitly the Laplace transform. It's less well known, apparently. It's I've never met this distribution before, but it can also be written explicitly. And you can do more. You have also formulas for conditional distribution of the volume during the perimeter, and more complicated formulas. all these limiting distributions are universal, okay? Meaning that here I have constants C and C prime. I could have written down the formula for these constants. They depend on the random lattice that you consider. I'm dealing with the IPT, but you of course could also consider the uniform infinite planar quadrangulation, which was mentioned by Timothy, or other random lattices. We expect that these formulas will still be valid, okay, with different constants C and C prime. Okay? Why are they universal? In fact, because they can be interpreted in terms of a continuous object, which is the infinite volume version of the Brownian map, called the Brownian plane. Okay? Just to explain this on a slide, how can you get the Brownian plane? Well, here I start with quadrangulations, not from triangulations, but I will say a word about that. If you start from a uniformly distribution quadrangulation with n faces, with the graph distance, this is the first theorem aesthetic. You rescale the distance by n to the power minus a quarter. In the limit, you have the Brownian map. But you can also do no rescaling and look at the local convergence, Jean-Franc convergence, when n tends to infinity. Then you get the UIPQ, the analog of the UIPT, but for quadrangulations. Okay? And now you can verify that you can also pass to the limit here just by multiplying the distance by a factor tending to 0, and then these objects converge in a suitable sense toward the limiting object, which is the Brownian plane, which can also be obtained directly from the Brownian map. You start from the Brownian map and you look at what happens locally near a point chosen uniformly at random. You blow up the distance by a factor now tending to infinity, and this converges to the Brownian plane. Okay, just like if you take the usual sphere and if you blow up the distance between one particular point of the sphere, well, of course, you converge to a plane, okay? Just a tangent plane if you want. Okay? So it's very similar. Well, presumably all this works also for triangulations, but this arrow here, this convergence has not been proved for triangulations. Okay, so the Brownian plane has many nice properties. In particular, in contrast with the Brownian map, it has a nice scale invariance property. Just multiply the distance by any constant lambda, you get a space with the same distribution. Okay, so maybe I will not say more about the Brownian plane. The last part of my lecture, I want to discuss this more recent work with Nicolas Curien. And the idea, which we already saw in the previous lecture by Timothy, is now to assign random length, or if you prefer random weights, to the edges of your planar map. Okay? And then you can define, of course, the weight of any path as the sum of the weights of the edges it contains. And there is a natural notion of first passage percolation distance, the FPP. The FPP between V and V prime is just the minimal weight of a path between V and V prime. Okay? So if you want, it's a kind of local modification of the graph distance. The graph distance is just the case where all your weights are equal to 1. Okay? And the goal now is to see that in large scales, this DFPP will behave essentially like a deterministic constant times the graph distance. Okay? Asymptotically, the balls for this first passage population distance will be close to balls for the graph distance. Okay, so let me immediately mention that, of course, if you try to do the same in the deterministic lattice, such as GD, this is not going to be true. It's not at all expected to be true. It's expected that you get an asymptotic shape for balls for the first passage population distance, which is not the shape that you get for Euclidean distance or for the graph distance, of course. But in some sense here, as we work with random planar maps, there is more isotropy, much more isotropy than for deterministic lattices. Okay? So this is the reason why we expect this. And an interesting consequence will be also, well, in some sense we increase the universality class of the Brownian map. We show that even taking other distances than the graph distance, local modifications of the graph distance like this limit will again give us the Brownian map. So the method for obtaining such results, at least the one I will present here, consists in discussing first the case of the UIPT. Okay? So I need to introduce what I call layers in the UIPT. And okay, so maybe you forgot the notation, I should have written that. This B dot R is not the ball, it's the hull of radius R in the triangulation. So you remember the hull was obtained by filling in the holes in the ball. Okay? So I'm going to be interested in hulls here. Okay? So this B dot R is the hull of radius R in my infinite planar triangulation. And here what I do, I fix two values k smaller than L, and I'm going to look at layers between the hull, well, I should say between the boundary of the hull of radius k and the boundary of the hull of radius L. Okay, so essentially my figure here, this object here, is just the hull of radius k, and the exterior boundary here is the boundary of the hull, the big hull of radius L. Okay? So what I call the layers are just all the sets, well, hull of radius j minus hull of radius j minus 1 for all j between k and L. Okay? So here I have a pink layer, blue, yellow, yellow, yellow. Okay? 3 layers. It's a case where L is equal to k plus 3. Okay, so I want to understand better this configuration. So what we do, we are going to consider special triangles in each layer. So this is what I call the downward triangles. Okay, these are triangles that are contained in certain layers. You know, b dot j minus b dot j minus 1 that have an edge in the exterior boundary of the layer. Okay, and then automatically, well, it can be proved. It's very easy to prove. The third vertex of the layer will be on the interior boundary of the layer. Okay, so for instance, let's take the last layer, the pink layer here. What I have done, I have kept the triangles that are incident to one edge of the exterior boundary. Okay? All these triangles here. So I color them in pink here. Okay? Then at the next stage, for the next layer, I keep the blue triangles here. Okay. So in this way, you don't get, of course, all triangles in the layers. Okay? There are missing triangles, which are there in white. Okay? So we get only the triangles in the layer that have an edge in the exterior boundary. Okay, so then what we do, well, we're interested in the combinatorial structure of these downward triangles. So I'm going to remove all the edges here which are not in the downward triangles. Okay, so I remove all these edges. So what remains is just a configuration of these downward triangles. And you have, of course, also white holes, like this one. Okay? And you should think that these holes have to be filled in some way, but for the moment I just leave them empty like this. Okay, so how can you describe such a configuration? Well, the nice thing is that you can describe this configuration by a forest of trees. So so something important will be that the trees are going to grow from the exterior boundary to the boundary of the small hull here. Okay. So if you want the direction of time for, if you look at the growth of trees, is the reverse direction of the growth of the radius of the hulls. Okay. So there is already a kind of time reversal which is similar to the one I had before when I told you about the scaling limits of the perimeters. Okay. So certainly the vertices of the trees are going to be all edges of the boundaries of hulls. So here I look only at hulls of radius j for j between k and L. The roots of the trees will be in fact the edges of the exterior boundary here, or the boundary of the hull of radius L. Okay? So in fact for each edge here of the boundaries of the hulls I will have a vertex. So I have drawn here on my figure 4 of them. And I have to describe now the edges in my forest. So what is the genealogical relation if you want to get my forest? So I say that this edge here, E prime, is a child of this one. This is why I have drawn here an edge like this. When I look at the white hole that is incident to E prime, so this is this white hole, it is bounded on the right by the downward triangle associated with it. Okay? So for instance, the same will be true for this this edge here. So this vertex here corresponding to this edge here. The corresponding white hole is the same before. So it is bounded on the right by this triangle. which corresponds to this vertex. So I drew also this edge here. Similarly, here I have a vertex here corresponding to this edge of the boundary of the hull. So its parent is going to be this one, because if I look at the white hole here, it is bounded on the right here by this triangle. Okay? So this is a general correlation, and you can now use this. You can draw all trees, if you want, that you get. So you have as many trees as you have edges on the exterior boundary, on the boundary of the hull of radius L. Okay? So some of these trees, of course, are trivial. Okay? This tree consists just of the root vertex, this 1, 2, but some of these trees are more complicated, this one, for instance. Okay. So now if you have a combinatorial way, if you want, to represent your configuration of downward triangles. Okay? And if you want to reconstruct, in fact, the layers, you only need to know the forest that codes the configuration of downward triangles, and also to fill in the holes. Okay? You have to say also what is in the white holes here. Okay, so this was just combinatorial description. So back to probability, what can you say? Well, now for the IPT, so I give a name here to my forest, coding the configuration of downward triangles, this script T1, script T2, and so on. I told you there are as many trees. The number of trees here is Pn, it's the perimeter of the external boundary, perimeter of the boundary of the hull of radius L. Okay? And then I look at the probabilities that this deterministic forest, to 1 to P. Okay? And there is an explicit formula. Maybe I will not comment too much about this formula. Well, essentially, you have two parts in this formula. The important part is this one. This is a product over all vertices in my trees, except those which are at maximal height. This is a detail of theta, certain function theta, of the number of children of the vertex V in my trees. Okay? So what is theta? Theta is determined by this generating function here. Okay? It's an offspring distribution. It gives you the distribution of the number of offspring of a given vertex, and it's characterized by this formula. Okay? So this part of the formula is really what you would get if you had a Galton-Watson forest. Okay? So a Galton-Watson forest is the case where you have independent trees, and they describe the genealogy of a population where each individual has n children with probability theta of n. Okay? So if you had only this term, this would correspond exactly to a Galton-Watson process. In fact, you have also this additional multiplicative term with an explicit function h, and this is in some sense related to the h processes we saw in the lecture by Timothy before. Here, this h should be interpreted as a stationary distribution for the Galton-Watson process with offspring distribution theta. And this factor corresponds, in fact, to a time reversal of the process. Maybe I will not say more about that. So the important thing is that you have this description, which is very close to Galton-Watson trees. So now the idea is that you are going to construct a half-plane model. Okay? So you construct a triangulation of the lower half-plane, it's important. So it will contain already all edges corresponding to the lines at integer vertical coordinates, meaning that you have the line here, vertical coordinate 0, -1, -2, and you have each of these lines, of course, you have edges between the two successive points with integer coordinates. Okay? So, and then for each horizontal edge, for each edge on one of these lines, z times -k, you will associate with this edge a triangle here, a pink triangle here in my figure, whose, which will contain this edge, and whose third vertex will be on the line immediately below. Okay? So you have all these triangles pointing below here, which I call again downward triangles. Okay, but of course you do not fill everything with these pink triangles. You are left again with white holes. Okay. And then what you say that you choose your configuration of pink triangles or downward triangles so that it is coded in the same way as before by a forest of independent Galton-Watson trees. Okay, so with the, I should have said before, with the configuration of pink triangles, you can associate a forest of trees with the same rules as before. Okay, so you see it's again the same. You say that, for instance, this vertex here corresponding to this edge here is a child of this vertex here. If when you look at the white hole containing this edge, it is bounded on the right by the pink triangle containing this one. Okay, so it's just exactly the same rule as before. So you can define the configuration of triangles so that the coding forest is made of independent boundaries. And then what you do, you fill the holes, fill in the holes with free triangulations with a boundary. So what is a free triangulation? Well, essentially, it means that the probability of a given triangulation with a boundary of the prescribed size with n inner vertices will be proportional to this quantity. Just, this 12 square root of 3 is just the growth exponent if you count well, it corresponds to the exponential growth of the number of triangulations with n vertices. Okay, so you define this half-plane model in this way, and why is it useful to consider this? It's useful because if you work with first passage percolation in this model, then it's easier to study. So you do what I explained before, you assign weights to the edges. For simplicity, I stick to this case, where weights are bounded above and below by positive constants. You define the first passage percolation distance. And what you can prove very easily in this half-plane model is the fact that if you look at the FPP distance between the root and the line at vertical coordinate minus k, so the root is supposed to be here, and you look at the distance between the root and this line, well, normalized grows linearly as k times to infinity, and 1 over k times the distance converges to a certain constant. Okay? And why is it easy to prove? Because it's just essentially the subadditive ergodic theorem. You have a subadditivity property which is very easy to understand. I think I don't have to explain the picture here, which gives you a bound for the distance between the root and the line at coordinate minus k minus l. It's bounded above by the distance between the root and the line at coordinates minus k, plus something which is distributed as the distance with the line of coordinate minus l. Okay, so you can use subadditivity and you get the convergence. Okay, so now I can come back to the UIPT. And the result we can get in the case of the UIPT, well, this is what I announced before. If we define, again, the first passage percolation distance in the UIPT, we have the fact that asymptotically, with a large probability, the ball of radius r in the UIPT for the first passage percolation distance will be close to the ball of radius r over C0 for the graph distance. Okay? So you can really say that balls for the first passage percolation distance grow like balls for the graph distance. And just to finish, what's the idea of the proof? The idea is really to use the half-plane model. You know? So this is a representation, well, this is supposed to be a representation of the UIPT, but you see vertically, I represent the distance from the root vertex. Okay. So here in red, what I have represented is the boundary of the hull of radius r. You see the difference between the hull and the ball. If I was considering the ball, I would have also a part of the boundary here, a part of the boundary here, but here it's just the boundary of the infinite connected component which is there. Okay? So what you say, you look at what happens just near the boundary of the hull. You zoom here at this part here, below the boundary of the hull, and what you see, because of all my results saying that while the layers are coded by trees which are almost Bolton-Watson trees, what you see here, just below the boundary of the hull, is something that looks like the half-plane model. Okay? So you can, well, this is really an approximation that is good enough to approximate, if you want, the distances here that you get in the UIPT by distances that you get in the half-plane model. Okay? So this is essentially the idea of the proof, and this is why the half-plane model is useful. Okay, and last slide. Now you can come back from the results for the UIPT, you can come back to finite triangulations. You use the absolute continuity argument, and what you get is you get the same scaling limit I had before. If you put instead of the graph distance here, this first passage percolation distance, and in the limit you get the same Brownian map, except that you have this constant C0, which is of course different. So just to say, last word of conclusion, in general, you cannot hope to compute C0, and well, it's because it's given by a subadditivity argument. But there are special cases where you can hope to do that, and we saw in the last lecture by Timothy Bell that he has a number of examples, well, not only for this FPP distance, but for other distances like the dual distance and so on, that you can hope to compute C0. Okay, thank you for your attention.
Okay, thank you so much. Last questions?
Yes. For the Brownian map, you talk about convergence taking only the metric into account, but for the I don't remember the name, when you're in the full plane and the infinite plane, you also consider things which are related to areas. And if I remember correctly, in the Duplanty-Sheffield and other guys' approach, they are unable to control really the distance. What they can control is a measure. So I was wondering if there was a possibility to have convergence of not only in Gromov, well, let's say in the sense of spaces for the Brownian map and things like that. I mean, to really make the connection between the two.
Well, the first thing is that okay, I've been lazy in the statement, and also in my paper I've been lazy because you can state the convergence in the sense of convergence of measured metric spaces. So that's very easy to do. Okay, there is a volume measure on the Brownian map, and it's a limit of the, if you want, the uniform probability measure on the vertex set. But you can prove all that. It's not at all a problem. It comes directly from the proof. Okay. So now, making the connection with the work by Bertrand and Scott Sheffield, yeah, so that's, of course, because they construct a measure, this UV quantum gravity measure, and of course here the problem is that we are not working on the sphere, we are working with an abstract random metric space, and so our measure is not defined directly on the sphere, so we would have to do to choose, if you want, a representation of the Brownian map on the sphere, and then maybe we could hope to identify with the volume measure in the work by Bertrand.
Just a simple question. Just a simple question. I missed the conditions on new, the distribution of the ID weights. Are there conditions on this new?
Yeah. Where did I put that? Okay. Yeah, here I'm putting these strong conditions, but essentially I don't think it's okay. I forgot to say all this part was a joint work with Nicolas. It was marked on the slides. Joint work with Nicolas Curien. So we think that it should hold under much more general assumptions. Okay. For instance, well, you should not allow weights that are too small. So maybe there is a condition on the tail near zero, you see. But for instance, if there is a bounded density near zero, I think it should work here. For instance, it should work for exponential weights. Okay. So here, in the paper, we have taken this, well, in the first version of the paper, maybe not the last one, we have chosen to work with this condition because it makes things technically easier. But I don't think it's necessary.
Any more questions? No? So, thank you. There'll be some last words by
Yes, we
the organizer.
yeah, some official acknowledgement and some unofficial.
Yes, so since it's the end of the conference, so we need to thank everyone who made this conference possible. So I will start with the speakers who gave a lot of very nice talks about different topics in random geometry. So I hope that it has helped to create some connections between people not necessarily the same background. I would also like to thank the chairpersons who help us keep the schedule as much as we can because it was really tight. I would like also to thank the participants who came in number and especially at this late in the afternoon are still very quite numerous. And so I would like also we have a slide on the persons and the institution who were before the conference started helped us. So yesterday I said a few words at the dinner, but I think I should do it again. So, but I will do it in the other way. So I will start with the people, our source of support. So we have been lucky to have private support from people like Daniel Jagelnitzer and Michael and Victoria Berczynski. And also we had a number of institutional support. So I think it's also important because behind this institution there are people who have been some of them working hard to get grants, apply for grants, and get us grants to help organize conference. So we have grants from Carta Plus and grants from Agence nationale de la recherche. There are local laboratoires d'excellence, so one in MAF, Adama, and one in physics, Palm. So it's good to see the connection between the two fields. And lastly, from Institut Physique Théorique, which we are funding from both CNRS and CEA, and we also have direct funding from the Direction des Sciences de la Matière. And beyond the money, then there is of course the organizational support. So thanks to all the staff from Institut Physique Théorique, and especially Mrs. Lorsevois, who is not there at this hour, but who is the person who took care of all the details in the background. Thanks to all.
Jeremy, you forgot a few people. If you forgot the three organizers, Jeremy, François, and Bertrand, who made this thing really possible, as well as well. Who concocted a very interesting and a very diverse program. I found that quite interesting, in fact, to see the diversity of subjects, and I'm pretty sure that Claude would have loved that, a mixture of math and various types of physics. So congratulations to the organizers for your request again.